So I'm astrophysicist, and today I will show our numerical simulation result about isotopic dichotomy. And also, I also introduce he is Yuki Masuda. His supervisor, he's also PhD student from Tokyo Tech. His supervisor is Tetsuo Yokoyama, and his analysis the nucleosynthesis isotope or refractory minerals, refractory inclusions in carbonation number. If you have interest about his talks, his topics, so please ask him. But today, there is a time limitation. I should talk about my topics. Okay. Okay, I said here. Today I will talk about this task related to this. I talk about in next slide. So yeah, let me start the introduction to this so sorry, sorry the window. So this figure shows isotopic nucleosynthesis isotopes of chromium chromium or meteorite. This figure shows there's a clear two groups in meteorites. So one is called for non-convex one. So the left one plot shows a group called as non-convex convert. Blue one is called for convergence. Also, this isotopic dichotomy suggests that there is two distinct dust reservoirs in planets like this figure. And so that is important to evaluate the origin of this dichotomy to understand solar system formation. And also, it is important to how these two distinct reservoirs accompanied by dust evolution. In a conventional dust dynamics, so dust particles directly into the central stress. So the energy dust reservoir is easily contaminated by tissue-like dust particles. So there is a mechanism to stop the radial drift of dust particles. One major idea to stop radial drift is irreducible. Irreducible formation. Sure. This figure shows this left figure shows numerical simulation or a gas disk embedded with Jupiters. This first point is a planet, and there is this figure shows the planet creates gas gaps by gravitation interaction between distant planets. And also, this right figure shows the gas surface density and radial distance. So, here is gas gaps. This gas gap creates structure of gas disks, and also this is important for gas dynamics because this structure changes the motion of dust particles. Okay, yeah. Without relation altitude, here dust particle drifted in central states. But at this region, because pressure gradient is different from different between here. So at this direction, at this region, dust particle quickly drift outward. So in that case, dash drifted to central stellar but the particle going back to this region. So this this drug structure cause the pilot of dust aggregate at this region. So the dust aggregate do not enter the region inside the interior to the planet. And so thus if there is a barrier of composition here, so this region is there dust particle like cycle like carbonaceous slide. This particle do not enter into the region inside the planet. So this mechanism keeps this mechanism creates two distinct reservoirs inside, creates the reservoirs region inside and outside. So in this seminar, the question and comment is always welcome. So please feel free to ask. So this is a conventional idea to distinct the dust reservoir by early Jupiter formation. But there is a possibility to break this idea because there is a dust rig. This is main topic of this talk. Dust aggregate actually pilot here, but dust aggregate experience multiple collision. Each collision produces small dust particles. Such a small dust particle easily pass through the gas gap because turbulence diffuses such a tiny particle easily. So if consider the fragmentation and diffusion, so large dust aggregate pilot here, but small particle pass through the gas gap. This leads to the contamination of energy-like dust particle into non-convergent flow-like dust reservoirs. So there's a question. So actually, the mass average Jupiter can keep the acidic dichotomy, or maybe this leak do not keep the distinct dust reservoirs. But this leak may be good for acidic dichotomy. This figure shows the accretion age and epsilon 54 chromium or meteorite. The orange cross shows epsilon 54 chromium value and accretion age for unconscious meteorite, and blue one shows carbonaceous meteorite. And Sear and Fuji's 2014 paper suggests there is a correlation between accretion ages and epsilon 54 chromium like this line. These are facet and elaborate if this is true, so dust leaking is leaking from the outer edge of gas gas is dust leaking for several million years. Previous study suggested. So concerning this leak, so the MC dust reservoir accreted relatively high epsilon 54 chromium dust for several million years. That leads the increase for epsilon 54 chromium for several million years. And also, if the tissue reservoir lost small particle by diffusion, the tissue reservoir lost relatively low epsilon 54 dust for several million years. So the loss which is increase or chromium or ceramic area because of relatively high dust remain in dust reservoir which has the dust remain in reservoir which has relatively high area. So maybe the dust leaking creates maybe there's a possibility to create dust leaking creates this correlation. So motivated these two topics, our aim is this. So we survey whether the early Jupiter creates isotopic dichotomy and correlation if it comes to dust leaking. To understand, to survey these topics, we simulate the evolution of dust size distribution at Epsilon 54 chromium with dust flows and fragmentation, diffusion in dust is embedded with gas from. And also we assess the time variation with chromium, LC and CC dust reservoirs. So the new, our new point is we construct the model to simulate dust size distribution, evolution dust size distribution simultaneously simulate the evolution of Epsilon 54 chromium dust particles. This is my motivation and this is my motivation. Is there any question or comment? Okay, I will show my methods. We construct a new model to simulate the evolution of dust size which we call chromium distribution in gas disk distribution. We model the gas disk embedded with Jupiter following these figures, and also we simulate dust size evolution without advection, radial direction of dust particles, and also we consider diffusion of dust particles, and also we consider the coagulation and fragmentation by collision of dust particles. And also we solve the evolution of distribution based on this method of this figure. We also initially give, and also we give the initially the inhomogeneous from distribution. So to consider the isotopic dichotomy, the details of this I will show next slide. And these are some parameters conditions. The main part of is main assumption is that initial Epsilon distribution. Actually, there is no clue to understand the initial condition for isotopic heterogeneity in solar level. So we arbitrarily set initial condition. The compiled data by I just call pressure, but Mercator some also suggests that Epsilon 15 chromium value or non-carbonous chondrite is high as -1, and also this paper shows that Epsilon 54 chromium for non-carbonous chondrite is less than 2. So considering these topics, I said arbitrarily Epsilon 54 chromium is -1 to 1 AU, and I said Epsilon 54 chromium 3 at 100 AU. And also we simply assume that for simplicity, we assume that initial chromium distribution is a linear function of relative distance. This is just assumption. So maybe we should update here. So in this talk, I said this right. And also we changed the some parameter from fragmentation velocity and turbulence parameter. This parameter controls the size of dust particles, size of the maximum dust particles, and also this parameter controls the efficiency of dust leaking. also strength, so turbulence strength also determines the turbulence, because turbulence diffuse tiny dust particle into the energy reservoirs. The next slide, I will show the result of my numerical simulation for dust size evolution and efficient deployments. This is this movie shows our result with case for dust rating. But actually, I think this picture is very different for everyone. So I'll explain. This picture shows dust. This picture, what actually shows the dust size. Horizontal axis shows like this. So, this picture shows that initially there is small particles. This small particle gradually go up, and also go upward. Also, this color shows the surface density of dust particles. So this colored region, so in this picture, this colored region dominates the total dust mass. These values. And also, this plot shows the efficient 54 chromium values on dust aggregate. So, like at this region, so the efficient 50 of chromium at this size and this. So these are values, average values. This picture shows average value of efficient 50 of chromium values. At this point, so the dust size, which is at 10 to minus 4, and at maybe 50 AU is efficient for high has a card or something. Yes, next slide shows the detail of dust evolution. This is a snapshot of dust evolution at 10 to minus 10 to 3 years. And initially, dust grew to the size determined by fragmentation, which is the size. In this case, the dust grew up the size at 10 centimeter size. Next, the grown dust aggregate is drifting into the center of cells. And the next slide shows a snapshot of 10 to 6 years. Yes. And so at this time, all dust particles grow up to the size determined by fragmentation or other mechanisms. And in this picture, you can see this color region. This region shows the dust aggregate pattern of this region. At this time, so dust aggregate grow up to the size determined by fragmentation or some mechanism, and directly the central cell, but due to gas gaps is here. Due to gas gaps, this dust particle go back to this region. So there is a color region. And also, this dust particle experience multiple collisions. This collision produce a small dust particle. And these dust particles raise from gas gaps. This such a small particle also experience collisions and they cause drifting centers. Space. So this is also main point is of this topic is the composition of dust. This is a picture of the efficient chromium at 10 to 60 billion years. In this case, so, the composition of dust at the region inside the gas gaps is has the efficient chromium value of 0.7 or 1. So this means that MC like dust so particle leaks drift into central star. So also this means this CC like dust particle drift into the MC results. So this is an example of my dust evolution simulation. To assess the correlation, we modeled to assess the correlation. We create a model to assess the correlations. Following the planetary formation theories, dust aggregate grow up to a planetesimal by the accumulation of dust aggregate. Yes, streaming instability or gravitational instability. So in this, I assume the dust aggregate and pile up for planetesimal at two regions. There we assess the aggregation of the point value at emission CC. For CC reservoirs, we directly derive the additional chromium value by the sum of dust aggregate at the region exterior to gas phase. So this region we directly derive the additional value from here, and also we average some value by the sum of dust region. But so in this calculation, we do not have any mechanism to form the accumulation of dust particle at the inner region. But in reality, there is a location to accumulate dust particle, like this inner boundary or something. So we calculate the actual problem value at actually determined by the sum of dust aggregate which passes through the inner region of our calculation. So we derive the actual for value for non-convergent contract derived by these all dust particles into the region. Based on this assumption, we derive the time variation of emission from value of MC and CC results. As the orange box shows the for reservoir for MC non-convergent conglomerate, the blue plot shows the reservoir for non-convergent reservoir. This picture shows the reservoir in efficient value increased with times for reservoirs for several years. But efficient value for coverage conglomerate increased until 1 million years. The reason why this trend is occurring is effect of dust rating. In our simulation, dust particles leaks for several million years. So thus the energy reservoir accumulates or dust particle which has relatively high efficiency value for several million years. Thus, this line increased for several million years. But at CC reservoirs, almost all dust aggregates are piled up at outside the gas giants, and also multiple collision homogenize the composition of dust particles. So emission reservoirs do not acquire the high efficiency value which are CC reservoirs do not acquire the dust particle which has high epsilon diffusion value for several million years. So this line, so the epsilon diffusion value is almost constant after 1 million years. And also we show the result without dust leaking case. The left figure shows the low turbulence case. In this case, the efficient value is almost constant because in this case there is no dust leaking, so the energy reservoir do not acquire the material which have high efficient values. And also the blue line is same because the same mechanism, same things happen in the case for previous missions. But this is a case for turbulence and poor stickiness case. In the poor stickiness case, the dust size is smaller than this case, and the time scale of wider drift is smaller than the time scale of wider drift is longer than this case or previous case. So in this case, dust pile up at the emission reservoir for several million years. So this blue line increases for several million years. And also in this no dust leaking case, epsilon 50 for chromium and energy reservoir do not increase for several million years. Finally, we discuss our result about dichotomy and correlation. Our result shows dust leaking could not homogenize between energy reservoir and CC reservoir because these two lines do not cross. So, and also our result shows that our result somewhat creates different value 3 million years to explain the single convergence conrad and also wave conrad. So we conclude very Jupiter could create isotopic dichotomy even if it considers dust leaking. And also our result shows that dust leaking can reproduce correlation between chromium value and ages at energy results. But in this case, we cannot reproduce correlation as CG results. This suggests, so to explain this, maybe so one possibility to explain this is formation of another pressure bands. If there is another pressure band outside of the Juillet, so the dust particle leak from other pressure band and contaminate the tissue reservoirs. So thus in that case, the chromium value is increased with time for several million years or something like this mechanism. So one possibility to explain the correlation between convergence conrad and age is formation of another pressure band. One possible mechanism to create another pressure band is the formation of Saturn-sized planet, because Saturn-sized planet can open the gas gaps in planet like this. This is a summary of my talks. We motivated by giant scenario, and we assess the time variation of chromium and CNC results by estimating the size and electron distribution. But we found that the isotopic dichotomy is caused by the Jupiter, even if it considers dust leaking. And also, dust leaking is important to reproduce a correlation between values and accretion age at reservoir several million years. But so we cannot reproduce correlation at CC reservoirs. So one possible mechanism is the formation of another pressure bump at this region. At the region exterior to the Jupiter device. Thank you for listening.
Thank you for this interesting talk. So I have questions for the speaker.
What about Titanium? Titanium. Actually, in this term, so if it's the same, yes, the same condition, so we can draw the same figure because the gas evolution is the same. Because same, but titanium for carbonaceous contour is higher than carbonaceous ones. So maybe we can create the same picture, but we have to check. We have checking it, and also maybe I have to concern about the abundance of carbonaceous acid, calcium aluminum leakage inclusion, because CAI has high abundance of titanium. So to consider to reduce the effect of the staking of titanium, it is important to the abundance of calcium aluminum leakage inclusion. Makes sense.
So you start with the old base. You do not consider it false.
Yes, do not yes.
So I was wondering, during the early stage of the disk, presumably we believe the CI form and the CIs are very rich in chromium 54 on average. So would that make a difference? Because in your model there is no size dependence of the isotopic composition. So at the beginning. So if you include chromium 54 rich CAIs, could it change things? I don't know. By the method.
So in this model, we can create the heterogeneity of acidification in minerals. So we are just thinking. So yeah, maybe initially we focus on so let's see. So in this calculation we cannot. But so we have maybe but we can yeah. So then the CF when drifting outward. Also, such a specific binary is resolved with pressure. Also, sorry, could you ask me again?
Well, I'm just, so it's a very open question now. If you include CAIs in your model, which is not the case right now, and with a very 54 rich composition, I don't know if they pile up rapidly at the pressure bump, and then maybe they collide, they grind to dust, maybe, I don't know.
Yes. So yeah, I make a point here. But we have to preserve the but so stickiness of particles depend on minimal size. Also, if it's a but yeah, I know, yeah, fine range here was some so if so, that is so in this models I cannot explain your question here. That's right.
So you mentioned the possibility of a second level, and in fact, perhaps there's also been previously suggested by computers, etc., that perhaps among the consistent light, an important dichotomy would be between normal consistent light and the CR plan. And in fact, when you show your plot the supernova Fujiyama, the two outliers, that as I said, and W011 are part of this CR plan. So maybe it's a possibility. Oh yeah, yeah. So if there is no second base, you see a constant average position in the C superplan. It is also true that it is a constant gradient. You still see a gradient in the outer disk. In the isotopic composition, you still see a gradient.
I cannot catch your question. Could you say that again? I cannot catch your question.
So, is there in the C, the outer disk, so the average isotopic composition doesn't change after 1 million years. But is there a special gradient?
Special gradient. Yes, there is. In this model, there is a special condition, but the total dust mass is not enough to form planet mass. Yes. So yeah, that is very good point. That's a special.
Because we could have believed that because the accretion time scale that it increases with distance, maybe it's just the way of accretion or it's progressive.
So related to the question, so are you showing the average value of chromium species of the parallel path?
Yes.
Only a parallel
Yes. Yes.
And so there is a
So there is a special gradient.
that you show that only
Around here.
A to 10A, right?
Yes.
Any other question? Yes.
I have a so we go back to the EK5. So yeah, number 5 slide. You show the information about the load. You say could see the loss, the load you shown for chromium dust for yes. Why? You mentioned that in the CCD about the lower chromium you show for chromium dust was lost, but but usually the lower dust can be lost faster than the higher anomalous dust, right?
This part. So you ask about why this value constant at this time?
I knew about. So you mean in this gradient of the electron chromium bio in the outer solar system, in the part of the CC region can fall into the inner part of the solar system. That's the idea.
Yeah.
Is it right?
Yeah, that's right.
Okay, so the other parts of the dust is preserved.
Yeah, that's right. That's right. Yes. Okay. So this is a preserved one. So, as this really. So initial dust particle distribution almost directly to the center of the structure.
Okay, makes sense.
Okay. Any other question? If not, we can thank the speaker again. Well, next seminar will be in September, I think it'll be Thorsten Kleiner, 28th. Voilà.